So this video that I'm making right now will mostly focus on chapter 5-2 on electric fields of charge distributions. And most of the things I'm going to be talking about here, I will assume that you are proficient in calculating the electric field for point charges and the different applications of those types of problems. And so if any of you guys are struggling on that, I can likely make a video on it before exam day, but please let me know on Discord or something. And yeah, we can do that. So starting with problem 7, because I thought it would be sort of a good introduction to charge distributions. And the big idea here is that we will be integrating Coulomb's law of electric fields. So just like how we have Coulomb's law for a point charge, we know that when dealing with one or two or a few point charges, we can sum the contributions of their electric fields at some point and find the net electric field. However, in the case of charge distributions, there are millions of charges that are distributed over some object uniformly, and so we can no longer add them up individually. So we must use integration to sum up the net contribution from the large amount of charges at some specific point. And you're going to see what that means in this problem. So in problem 7, we can see that they have not given us a picture, so we should start off by doing that. And so now it says that it is a negative charge of big Q, meaning that anywhere on this plane the electric field vector will point inwards, or in other words towards the charge distribution. So if we are at the origin, let's make this pink point P, the electric field will be, or the net electric field will be pointing like this, sort of at like a 45-degree angle. And our E sub x will be straight to the right. E sub y will be straight up. And to help you visualize this, you can just imagine that, every one of these like little pink bubbles that I'm drawing, each of them is some negative charge. And so if point P is here, that means that we have an electric field vector that's individually for each one of these charges. So for this charge right here, you'd have this vector. For this charge right here, you'd have this vector, this vector, and so on. And each of these vectors will have to be split up into components of x and y. And once you sum the contributions of each of them to their respective component, you would have just one big arrow going in both the x and the y direction, and together as one vector combined, they would form this net vector that we've shown right here. So that is how part A would look. And so let's move to part B. So what we are going to do here is we're going to do what we always do with the vector, which is split it into its x and y components and sum the net contribution from each vector. And this is very key because some students think that splitting the integral into components is useless, or some might think that we only took two individual vectors from the center pointing up and to the side, and a vector to the side, and ignored everything in between. But what we were really doing is we are taking each vector from the many charges and splitting them into components so that we can integrate them correctly. And if you don't do this, then you will just be adding magnitudes of each vector, not taking into account the direction. So let's see how that looks. So these are our equations for the charge distribution question. And basically what I've done here is I've taken our original electric field equation from Coulomb's law, E equals kq over r squared, and I've just made it into something that we can integrate. So now that we know what's going on visually, let's focus more on what's going on the math side. So key things we'll be looking at here will be the integration bounds and our differential. So starting with our dq here, we want to be able to integrate this, but there's a problem, being that the electric field that we are summing up here does not depend on just the charge amount, as we just went over, right? Each of these vectors have a direction, a magnitude and a direction. And so we have to take into account that directional aspect. And so we have to make our integral take that into account. So this is where our charge density equations come in. So we know that, so there are many of these equations, but roughly what we know is that lambda, or whatever density you're using, whether it's sigma, rho, whatever it is equal to the total charge over the length, or the area, or the volume. Over here it's length because it is just it's a line of charge. It's like an arc, so it's not some surface area or some volume. And so what we want to do here is, since we're trying to find some substitute for Q, what we're going to do here is just, we're going to, instead of saying lambda is equal to the total charge over the total length, we're just going to say that lambda is equal to some infinitesimal small step or amount of charge over some infinitesimal small change in length. And these, regardless, these are the same. It will still equal our lambda. And so moving this around, we have dq is equal to lambda times dl. And so substituting this in, dE sub x is equal to the integral of k over r squared lambda dl cosine of theta. Now from here you might be thinking we are done with our substitutions and we can integrate now. But not necessarily. We still are not done. And that is because the direction of the electric field vector depends on the angle at which it is, or in other words, dl only tells me I am moving along this arc of charges, right? I'm summing along this charge, wherever, from whatever this point is to whatever this point is. But it does not tell me how my electric field vectors from point P are changing as I do it. And so we use the arc length formula to set up an equation that relates L with theta. And that looks like this. dl is equal to our radius, not changing, multiplied by d theta. And so now when we substitute this equation into this integral, we have k lambda, we have k over r squared lambda dl, or lambda r d theta, multiplied by cosine of theta. And on this side, dE sub y is equal to the integral of k over r squared. And then writing the same thing, lambda r d theta, multiplied by sine of theta. And yeah, and so now after substituting all these equations in, we can finally integrate this. And because we are integrating with respect to d theta, our bounds go from 0 to a quarter of a circle, or pi over 2. So and we can take out all of our constants. And so the sine of pi over 2 is equal to 1. Sine of 0 is equal to 0. And so we just have, so this whole thing just equals k lambda r over r squared multiplied by 1. Lambda in this equation is equal to, as we know, it's equal to Q over L. And we know that L is the circumference of this circle. So the circumference of a full circle is 2 pi r. So divided by 4, and we get the circumference over this arc right here, which is pi r over 2. So we get Q, and then pi r over 2, which is equal to 2q over pi r. If we substitute that back in here, then we get k over here, k over r, multiplied by 2q over pi r. Pi r squared. Okay. And so likely we're going to see something very similar on this side. So everything here happens pretty much the exact same thing. K lambda r over r squared, integral of sine of theta from 0 to pi over 2. This is equal to negative cosine of theta. So all these little like integration things that you have to memorize. Honestly, any equation here, you could just throw that on your cheat sheet. That way you don't have to like learn the conceptual aspect to it. So there's that. So this is equal to, so cosine of pi over 2 is 0. So negative 0. And then cosine of 0 is equal to 1, so negative 1. a negative times a negative equals a positive. So this is equal to positive 1. And so we see that it's pretty much the exact same thing. Lambda is equal to, what was it, 2q over pi r squared, I think? Is that what I was learning? Yeah, lambda, or 2q over pi r. And so substituting that into our equation with k over r multiplied by 2q per pi r. And this right here is equal to 2q k over pi r squared. And so we have e sub x is equal to e sub y, which is equal to 2q k over pi r squared. And so to take the magnitude of this, or I suppose, I don't think yeah, so this would actually be our final answer. Sorry.